Welcome to IOS450, Building an ObjectiveC Bindings Library. In this course, we are going to look at how to bind an iOS library manually, and then we're going to look at describing frameworks and libraries in much more detail so that we understand how to consume these appropriately. So by the end of this class, you will be able to describe the main differences between the library types that you would use in Xamarin binding libraries. And you will also be able to describe what is involved in manually binding an iOS library, as well as creating a simple class binding. Creating Xamarin iOS binding libraries are generally perceived as a complex endeavor, and this really should not be the case. In this objective, we are going to look at binding a simple class, and we're going to do this step by step. And as we do this, we'll demystify the process. Now, before we get into any code, there are a few additional concepts to cover. First, we are going to look at how to consume static and dynamic libraries. Next, we'll talk about ObjectiveC, and just enough to define ObjectiveC messages and selectors and get us going. And then finally, we will create a CSharp wrapper class and register this class with the iOS runtime so that we can consume it. Apple publishes frameworks and libraries with rich APIs targeting iOS, Mac OS, and tvOS. And you have already used these frameworks in your own applications. For example, if you created any application using standard iOS controls, you would have used UIKit. And Xamarin exposes these frameworks as .NET Managed Class Libraries, which you are able to use in your C# and F# language-based applications. However, there are also a large ecosystem of third-party libraries and frameworks supporting devices and services not distributed as part of the main OS. And this is on each of the Apple devices that we might own. So these libraries, for example, often include items such as additional non-Apple vendor-specific services, or additional mapping support, or even access to external devices. Xamarin, however, does not expose these frameworks outside the standard Xamarin iOS distribution. And this includes tvOS and Mac OS as well. Which means if we want to support these libraries or consume them in our own applications, we're going to need to either bind these libraries ourselves or figure out some other way to consume them. To put some context around all the theory that we are going to cover, during the process, we are going to bind this LM gauge view. The LM gauge view is a project written in ObjectiveC, and it provides us with a library that gives you access to this gauge view. We'll look at the code in Xcode, and then we'll see how the code performs when bound in a C# implementation. I've got the project loaded in Xcode, and what you'll notice is that this project comes with two parts: the actual library definition and implementation as code, plus the demo that will show us how to run this and just get a sense of what this gauge view looks like when it's actually executed. Now I'm going to run the demo so we can get a feel for the application, and then we'll come back and have a look at code. Once the gauge is loaded, you'll notice that it seems to drive itself. Now my guess is there's a timer in the background which will then update this value. You'll notice there's a minimum value, a maximum value set, and it seems to be that there's a threshold property that we can manage as well. In terms of this demo, there's this switch which allows us to switch to a dark background and back to a lighter background. I've got the project loaded in Xcode, and what you'll notice is that this project comes with two parts: the actual library definition and implementation as code, plus the demo that will show us how to run this and just get a sense of what this gauge view looks like when it's actually executed. Now I'm going to run the demo so we can get a feel for the application, and then we'll come back and have a look at code. Once the gauge is loaded, you'll notice that it seems to drive itself. Now my guess is there's a timer in the background which will then update this value. You'll notice there's a minimum value, a maximum value set, and it seems to be that there's a threshold property that we can manage as well. In terms of this demo, there's this switch which allows us to switch to a dark background and back to a lighter background. Let's look at the code next. Now in terms of this implementation, the view controller is going to show us the logic that drives the actual app. In here, you'll notice there's a couple of colors set. There is a couple of UI controls that are set up as outlets. And then we have a bit of logic in here. In my view.load method, you'll notice that we have minimum, maximum, and a limit value set up, kind of what we saw in the view itself. And then there's a timer that seems to update the view as this timer ticks. Now the rest of this is purely implementation details, just to get the color switched to dark and light, so we're not going to spend much time on it. And it may feel at this point that recreating this gauge potentially in CSharp might not be that much work. To prove that statement, I want to look at the gauge view itself, and we'll start with the header file. The header file is going to indicate, to me at least, how many properties and what the API looks like to engage or instantiate the gauge view and then actually interact with it. And as you can see, there seems to be quite a bit of properties available to us. There's also a delegate. So my willingness to go and rewrite this in CSharp is definitely waning at this point. If we look at the member file, you'll see that there's actually gone quite a lot of work into creating this gauge view. So definitely at this point, rewriting this in CSharp is a no-go for me. I would rather like to use the library as is and wrap it in a CSharp wrapper class so we can consume it from a CSharp app directly. Here is our CSharp version of the library loaded, or at least the demo that consumes the library. You'll notice that we have a storyboard. In our storyboard, we have a single scene with a slider, and we're going to use the slider to update the gauge's value. Now, there's a couple of things to keep in mind. You'll notice that the slider is added first, and then we're going to add the gauge via code, which means the gauge is going to overlap based on the bounds, the actual slider's placement. And therefore, you'll notice that on line 27, I'm going to use bring subview to front so that the slider Z index gets altered and it now gets displayed in front of the gauge itself. You'll see that we are able to instantiate a gauge, we are able to set its frame, we're able to set a delegate, we're also able to set properties. If we look at the application running, you'll notice that the gauge itself seems to interact exactly in the same fashion as it did with the Xcode project. And the reason why it's this is because it's exactly the same library. So instead of writing and recreating the actual project itself, we've decided to bind to the library and we just consume the library as any old object. Now, that does sound a little bit too easy, and in a way it is. There is this binding class which we need to look at. This binding class is basically the definition for us to expose a CSharp API that overlays an ObjectiveC API, and you will see things like registration attributes. You are going to see that we have pointers that points to objects. You have export attributes. These export attributes allows us to expose members. Now, there's a lot of information in this file, in these couple of lines that we see here, and you're not supposed to understand any of this at this point. Let us go back and let's go and look at the theory, and then we'll see if we can get to the point where we are able to write this code ourselves. The ObjectiveC code that we've just looked at is not going to serve much purpose unless we understand how to consume this. So we need to understand what a binding library is. A binding library is a specific Xamarin project type, which is going to allow you to wrap one or more ObjectiveC frameworks or libraries into managed assemblies. These frameworks and libraries could be from third-party providers or even ObjectiveC libraries already in use in your organization. For example, let's assume you want to use an existing ObjectiveC library, and you want to use this library on a mobile device in your own Xamarin iOS application. You can now decide to rewrite the library in CSharp, or alternatively, you could rather create a CSharp managed wrapper for this ObjectiveC library, and then use this managed wrapper instead in your application. For today's class, we're going to focus predominantly on iOS bindings. However, the concepts that we are going to discuss are similar for Mac OS and tvOS bindings. Let us start with how we access libraries to understand the process that's now going to be involved. When you create an ObjectiveC or Swift-based application, accessing native objects are straightforward. You're going to reference the framework, and you'll then immediately be able to code against the new APIs that have been exposed. Normally with Xamarin iOS, the process feels the same. You reference a library, add your namespace, and then again code against the API. And this is true for all Apple provided frameworks that we have access to, generally speaking. The reason for this is that Xamarin iOS has already provided us with a layer which maps out the CSharp APIs to the ObjectiveC APIs. However, our library does not have this layer and we'll need to provide it. To do this, we are going to create a managed wrapper API that will allow your application to access the unmanaged API via it. And this wrapper API is going to be coded in our example today as a C# implementation. Your application will now be able to reference the managed library code that we've just created in the wrapper and then access the native API via that project reference. With Xamarin iOS, the libraries that you are going to access will be primarily written in ObjectiveC. However, there's nothing preventing you from binding C or C++ code indirectly. Let's go back to our C# code from earlier. Now we know this is the binding library, and we know that we expose a C# API, and we know that we are drilling into an ObjectiveC API. Now what we saw here is that we have this class. There's a lot of stuff happening on this class, which we'll talk about. But I want to simplify this a little bit. Before we get to this part, we actually go and execute C, or rather ObjectiveC code. I want us to look at the basics, and some of you might have seen this already. This is where I am going to make use of Invoke. I want to scroll down here a little bit. And you might have seen this where we have a DLL import, we have an entry point into a library, and then we have some code that will be executed. And we're going to start off at this level. Then we'll build to the point where we actually are going to allow ObjectiveC messages to be sent and received. In terms of building the C# wrapper, there are three major steps involved in the process. First, you will create a C# class which will hold the C# API you would like to expose. Then you will need to identify the API from the native library which you need to expose and decide what the equivalent C# API would look like. Once you have that in place, you will create the mapping between the C# API and the native API. And it is in this mapping process where a lot of our work will reside. When you need to access unmanaged functions from managed code, you will make use of Platform Invoke, or Invoke for short. Platform Invoke is available in all managed languages. Both Android and iOS allows access to methods defined in C or C++ libraries. And here specifically, we will be using Mono's Platform Invoke to facilitate this functionality. Remember, when we compile our applications, we use Mono as the runtime. In this model, there is a couple of interesting components which we should take note of. To start off, managed source code is going to be compiled into intermediate language, which is executed typically by the CLR. In our case though, when we use Xamarin iOS, a native binary will be created. So there's a slight difference there. However, to access unmanaged code, the Invoke mechanics will be used. Right, so this is used to identify these functions that we would like to target. And this is done via method attributes, which we will look at a little bit later. What you need to keep in mind is that a standard marshalling service is in place. Marshalling is the process of transforming the memory representation of any of our objects to a data format suitable for storage or transmission. So this means that marshalling is typically used when data must move between different parts of a computer program or from one program to another. The important aspect to note here is that with marshalling, the intent here is to maintain the class definitions of these objects that we are going to use. In our case, the conversion between an unmanaged type and a common language runtime type. There are a few steps we need to cover in terms of the process of implementing Invoke methods in a wrapper library. The first step is to decide on the function you would like to invoke. The second step is to define the API signature as you would like this to be exposed in your C# code. The third step is to determine in which library this function will live. And then lastly, we'll write the appropriate Invoke attribute declarations so to map the C# method call with the actual invoked method in your library. Let's assume that we would like to draw a frame around the inside of a rectangle. Once we start looking at the API documentation available for UIKit, we found that we would be able to use UIRectFrame using blend mode to achieve this. Now this method allows me to draw a frame inside the rectangle defined with a specific fill color and a specific blend mode specified as part of the context. Now there's a couple of things here that's interesting. You'll notice that we have two very specific parameters that needs to be passed into this method. And we're going to assume that if we want to consume this UIRectFrame using blend mode method, that we have those two types already defined and accessible to us. So this is the first step. We've now defined the function that we would like to invoke. Our next step is to define the API as it will be used from within the managed code. So the CSharp API that we are going to expose. There's a couple of things here that's also kind of interesting. First off, notice that we have two very explicit keywords specified here. The first one being extern and the second one being static. Extern means that the function is imported from C or C++, and static is going to indicate that this function has no knowledge about the class, in this case, let's say program, in which this call is defined. Also note that we, like before, are going to assume that we have the C# types available that's required to match the input to the underlying library call that we are going to make. Once the member signature has been defined, you need to specify the library this function is invoked from, as well as the entry point of the function inside the library. In this case, the function's name. Notice the use of the constants in this example. These constants are used as convenience mappings to the physical paths of the libraries on the device. The last step is to place the code in your managed code library. We've made a decision that we would like to have this method live in shapes decorator, which is going to be a static class giving us access to our API. Up to this point, we've really just focused on p-invoking functions residing in static libraries. But we also have the opportunity to access functions in dynamic libraries. Dealing with dynamic libraries is generally speaking the same as with a static library. However, there's one big difference. The Xamarin iOS runtime must load the dynamic library first. After that's done, we'll then be able to proceed with our standard p-invoke declarations. To access the dynamic library, you need to load the library first. This step is done via the Xamarin iOS framework. The dlopen method is used to load and link a dynamic library, and it returns a handle that can be used with either dlsim or dlclose. dlsim is used to obtain the address of a symbol defined within the object made accessible through a dlopen, and dlclose informs the system that the object referenced by handle is no longer being used, which means it can be let go. The first parameter to this dlopen method is the actual physical path to the file which should be loaded, and the second parameter is the mode in which the library will be accessed or loaded. The mode that we have here is mode 0. That's the default mode, which means that this library will be lazily loaded and bound the first time the function is required from it. For the most part, the rest of the implementation follows the same steps as the static library process. You will notice that we have our class definition. We have a DLL import attribute definition with two parameters. The first being the library that we're going to use, and the second being the entry point into this library for the function that we would like to use. Then we have a specification for the C# API, decorated with the static and extern keywords. Generally speaking, the libraries that you will consume will be in the form of a compiled binary. As developers, you need to know what classes and methods are available to use from these libraries. This means that the interface to this library needs to be defined. And even though you have tools available to you which will provide you with a name list or a symbol table for this library, it's not remotely convenient to use. And therefore, the concept of an API exists which describes the behavior of a system. In addition to convenience, the separation of the API from its implementation can allow other languages to then use this library that's potentially written for a different environment. Both C, C++, and Objective-C implements this concept of separating the API from the actual implementation. This requires the developer to create what are called header files. As an example, look at the weather class definition on the left-hand side of the screen. Here we have a header file that describes the API, whereas the M file, or the member file on the right-hand side, is going to show us the implementation of what this class would look like. Now, what you would have noticed here is that there's a one-to-one relationship between a header file and a member file, or the implementation file. Complex libraries and frameworks can potentially include any number of header files. However, the prospect of managing multiple libraries is neither exciting nor convenient. As a result, Apple Frameworks makes use of a single header file, which references all the other header files that is relevant to this framework, and then allows us to hook up against this. So for example, instead of referencing each class independently, when you create your UI elements, you would rather reference a single framework header. A few aspects to keep in mind when working with umbrella headers and frameworks is that when binding frameworks, the umbrella header file will have the same name as the framework, which is convenient. It is typically only required to bind against a single header file. However, this may not always be the case, and there will be instances where you are going to need to change the header file by hand. We'll investigate these scenarios in much more detail later on in this course. It's time to look at code again. We've learned that we are able to p-invoke static libraries, we are able to p-invoke dynamic libraries, and if we look at our code here, there's something that, at least for me, is kind of interesting. Notice that it seems, and I'm going to scroll quickly through this code, notice we are going to only call into this dynamic library. So each of these methods is going to allow us to p-invoke, but into a single dynamic library. Our GaugeView library is a static library. So the question is, what is going on here? So that's the first thing we need to think about. So dynamic library, static library, and if I look at the other code that I have here, this LMGaugeView class itself, there's no p-invokes in here. The base class does not seem to be any in here, neither in the delegate. Let's head back to this messaging class. So this messaging class is going to basically do what it says, send messages. So look at this. We have an ObjectiveC message sent, send super, there's another send, and the only thing that's different here is the parameters passed to this method. We'll need to dig deeper into this to understand exactly what is happening here. If you were not dealing with iOS, we could stop the discussion right here. However, you will soon realize though that working with Objective-C is not this straightforward. The interesting thing about Objective-C is that the method invocation is done via messaging. Right, so what this means is, assume that you have a class which implements a method which takes a float as a variable. So to execute a method on this class, you're going to use the basic Objective-C syntax that uses square brackets to indicate which method needs to execute. In here, you're going to specify the receiver of the message, right, so the class. Then you're going to specify the method on the class that you would like to invoke. And then we'll specify the parameters to this method. At the end of the day, this message now gets sent to the receiver class, which will then execute that method if it exists. Let's add some context to this by comparing this execution with a CSharp example. Assume you want to execute a method on a CSharp class instance. You would write code that looks like this. Now, if we compare this to Objective-C, the code is going to differ quite a bit. With Objective-C, the majority of the work done in your application happens as a result of a message being sent back and forth between objects. You need to keep in mind that there are several ways to send messages in Objective-C, but this is the syntax that's most commonly used, using square brackets. So let's break this down. On the left-hand side, you have a reference to an instance of a weather service. This is the object that is going to drive the functionality that we are looking for. And it's going to be the receiver of this message. On the right hand side, you have the message itself. Right? So here we have the fetch weather. That's our called selector, which we would like to execute. Basically the name of the method that's going to be called on the receiver. When this line of code is executed, the temp weather service is sent the message fetch weather. When creating Xamarin iOS bindings, you will need to make use of the same concepts. Unlike normal C# functions and C++ member functions, you cannot directly invoke a selector using pinvoke. Before we continue, let me define the term selector I've used on the previous slide. Method names in messages are often referred to as selectors. A selector is the name used to select a method to execute for an object. You can also think of a selector as a unique identifier that replaces the name when the source code is compiled. The compiler will ensure that all selectors are unique with this process. A selector is created from a string and is used when you want your code to send a message whose name you may not know until runtime. And what makes a selector useful is that it acts like a dynamic function pointer. This means that for a given name, this pointer automatically points to the implementation of a method which will be suitable for whatever class it is used with. However, by itself, a selector does not do anything. It only identifies a method. The question now is, how do we implement this mechanic in C#? Let's go back to our example. The fetch weather method, or our message in this case, needs to be sent to a weather service instance, vacation weather service. And as we're starting to see, in ObjectiveC, messages are not bound to method implementations until runtime. So it is going to be the compiler that converts a message expression into a call via messaging function. And this function is ObjectiveC message send, which is a function that has a simple return value. To accommodate various method signatures, ObjectiveC message send has several overrides with a simple return value that sends a message to an instance of a class. As you might have guessed, based on the function name, ObjectiveC message send is a function found in ObjectiveC libraries. More specifically, the ObjectiveC runtime library named libobjc. This is an API used to develop a link between ObjectiveC and other languages. And functions from this library are implemented in a shared library named libobjec dilib. Since ObjectiveC message send is not directly exposed in Xamarin iOS, there are two steps you will likely need to take to access it. The first step is for you to create a pinvoke statement. The second step, however, could result in a couple of lines of code. This is depending on the override that you choose for the relevant return type needed. For example, here we're returning a reference back to another object instance. This means that you'll actually have several invocations depending on the return type. The Mac OS implementation of the ObjectiveC runtime library is unique to the Mac and available via Xamarin Mac. If you decide you would like to bind Mac-based ObjectiveC libraries, this is the implementation to use. Once you have defined your pinvoke implementation, you are basically ready to get going. Let's recap. This is the class level definition of the method you wish to execute. This is defined in ObjectiveC. Using ObjectiveC, your syntax would look like this. You are now able to recreate this message using the following C# code. But watch out, this code seems misleadingly simple. You'll notice that we need a pointer to the instance of the class which is the target to receive this message. And you also need a selector instance for the string name of the selector. I want us to pause here for a couple of seconds because there's something that personally doesn't sit right with me with what we've done so far. If you look at this code, what's going to happen here is that I would like to instantiate a version of this vacation weather service in C#. Then I probably would like to execute a method called fetch weather on this service. But so far we've just implemented pinvoke statements. There is no way for me to instantiate this object. This means that we need to dig deeper into how these libraries are going to be registered so that we can consume and expose them in C#. In addition to consuming our libraries, we also allow these wrapper classes to be exposed to the native libraries. This means that we would like our object to behave as an ObjectiveC object. We would like to manage messages and selectors, and we would like to register this class with the iOS runtime. Keep in mind that you'll not only bind methods, you'll also need to bind a class or classes so that you can instantiate and interact with these class members. This means we need to understand a little bit more about ObjectiveC classes in themselves. The root class of all class hierarchies in ObjectiveC is NSObject. Any object inheriting from NSObject is going to ensure that this object is inheriting a basic interface to the runtime and the ability to behave as an ObjectiveC object. In addition, the object has all the methods called to an ObjectiveC object. Right, let's head back into code because I want to explore this a little bit. What we've just heard is that the Invoke part to our implementation here is going to allow us to send messages. So it gives me access to object message sent. Now, if I want to expose a class, then I will need to indirectly or directly inherit NSObject. So this means that if we look at this binding lmgauge view, this class is currently being exposed, and we do a bit of registration, exporting of members and properties. Okay, so what I think we need to do is we need to break this down to something a little bit simpler. Let's create, and this is just for example's sake, let's create a new file, and we're going to inherit from NSObject. So let's call this the engine, right? So the engine is going to make use of a class, and that class's name is, what shall we call this? The wheel. All right, so the wheel is going to be used inside the engine, and if I do something like this, then my wheel's properties, so if I go var wheel equals a new wheel, or the new wheel, then I would have the following options to choose from if I looked at the properties here. So wheel, in terms of the IntelliSense suggestions, will just show me C# object properties and members exposed. Which is okay, I mean that's what we normally use. But look at what happens if I change this. If I change the wheel, and I say wheel, you now inherit NSObject, and we make sure that we reference the correct namespace to include this, so foundation, then you will find that wheel now suddenly supports everything from the ObjectiveC world. So you can see there's a class handle, conforms to protocol, what else? Debug description, description to change, there's a dispose, that's kind of interesting. What else? Let's see if we can find a handle. Yes, there's even a handle. So as soon as I start using NSObject, I will have access to its ObjectiveC representation, which means this object can now be moved from C# to the ObjectiveC world and back to C#, which is pretty cool. Now with this in mind, let's go back to our theory and see what's going to happen next. Xamarin iOS provides you with the same NSObject class implemented in C#. What is very important here is the following. First, an object that derives from NSObject is a managed representation of the underlying C# instance. Second, this class provides an NSObject handle property which contains a pointer to the unmanaged ObjectiveC object. NSObject is a complex class. However, there are a few relevant methods when dealing with selectors, and which will now be available on your NSObject derived instance. First, you'll notice there's a respond to selector. This is going to allow you to test whether this object recognizes the specified selector. You will also find a perform selector. This is going to allow you to perform the specified selector. And then lastly, there's a get method for selector, which returns the address of the receiver's implementation of a method so that it can be called as a function. In order to make an ObjectiveC object available in C#, you need to create a C# wrapper class for this object in question. However, as you will not only consume these objects from the ObjectiveC runtime, but also pass these objects back to the runtime, the object needs to be accessible to the runtime. Deriving a C# class from foundation in its object will create an object which can be passed back to the ObjectiveC runtime. Interesting to note is this automatic registration will register the class with its name as you've designated it, but there will be a prefix added which includes the namespace to this class. To achieve this registration, Xamarin iOS makes use of a type register system to not only make a class available to the ObjectiveC runtime, but also members of this class. However, there is an exception. Some members are automatically exposed. Specifically, all overridden methods from the ObjectiveC class will be exposed. Important though, it's only going to be the methods that are exposed from the class. Your own members, that's defined in C#, will still need to be registered. Let's go back to our LM GaugeView class. So this GaugeView class is going to be exposed to the ObjectiveC runtime because it ultimately implements NS object. Now that might be not that apparent right now. So let's do this. Let's dive into the UI view that we're inheriting from. UI view implements a class, UI responder, and then a couple of interfaces. We're interested in this base class, UI responder. And if we dive into UI responder, you'll see that it ultimately implements NS object. Right, so that deals with NS object, and that's kind of why this class will be exposed. Now, if that's the case, then it means that we should have members here that are available to us as soon as we override them, which automatically gets exported or set and registered with the runtime. So set needs layout is one of those examples. And if we dive into its definition, you'll see that this is the virtual set needs layout, and that's the export for it. So that's kind of interesting. This means that these attributes are then responsible, based on what we can see, are responsible for this registration. Let's dig into this. Let's see if we can figure out how many of these attributes are available and what they are going to allow us to do. During application startup, Xamarin iOS will register all attributed C# elements via the Xamarin iOS type registration system. Each attribute is specifically designed to manage and map C# concepts to ObjectiveC and back. Register is used to map C# classes as ObjectiveC classes. Export is used to map class members, where protocol maps interfaces as ObjectiveC protocols, and category maps extension methods as ObjectiveC categories. In the case of bindings, the register and export attributes are of particular interest to us, and we will investigate these over the next couple of slides. The register attribute has three primary functions when creating bindings. It allows you to rename a class. It allows you to identify the class as a wrapper. And it services all the members of the class to the iOS designer. To set a class name, you will be able to use the register attribute. Here's our example. With this attribute, you are able to override the exposed class name. When registering a class, we are able to specify its name with the register attribute. And this will indicate that we have a C# class that needs to be registered with the ObjectiveC runtime. However, if you have a C# representation of an existing ObjectiveC class, we're going to need to use a second parameter. And this parameter's name is wrapper. This is going to indicate to the runtime that this C# class wraps an existing ObjectiveC class. I want us to explore adding these attributes in code. We could decide to leave this class as is with no registration, because as we saw earlier on, the base class of UIView is NS object. The problem is though, the registered name normally then just includes the actual namespace concatenated with the class name, and that's not going to be what we're looking for. We're going to rather use at this point the register attribute, specify the class name itself as a parameter, and then we're going to specify that this class is a wrapper class. So this means there is an ObjectiveC class underneath that we are going to access at some point in time. So for now, we'll specify the second attribute property to true. As you have now seen, the register attribute is used to register a C# class to the ObjectiveC runtime. Even though this might be obvious, a C# class is not automatically surfaced to the ObjectiveC runtime, and you have two options to achieve this. You can automatically surface your class using NSObject, but there are limitations because the members are not automatically surfaced. Or you can surface the entire class to ObjectiveC runtime manually using the register attribute. As I've mentioned before, C# class constructors, C# methods, and C# properties on your class is not automatically surfaced to the ObjectiveC runtime. You use the export attribute to expose these members. It is important to note, C# methods, properties, and constructors are exposed as methods to be invoked from the ObjectiveC runtime. The export attribute allows you to expose a constructor of an NSObject derived class to the ObjectiveC runtime. In this example, the constructor exports the default ObjectiveC class initializer. I want us to explore the default constructor implementation for a couple of minutes. First, generally speaking, when I implement a default constructor in C#, it's going to look like this. My constructor without any parameters and no base class implementation. However, we now know that we use NSObject, which means we are going to have to implement our constructor in the following way. We'll use an NSObject flag, but we'll pass an empty instance value to this constructor. The next thing that needs to happen, this default constructor needs to initialize the actual ObjectiveC class itself. And now the question is, how are we going to achieve that? Because at this point, nothing like that will happen. And the answer to this is the implementation of the NSObject's initialize handle method. Initialize handle is going to make sure that we initialize the object via the proper constructor. So we're going to call the init method on the ObjectiveC class itself. And this is what our code will look like. Initialize handle. Right, so once you specify initialize handle, you're going to need to provide a pointer. Since we need to call a method, we're going to have to now make use of our messaging class. So at this point, this is what our method looks like, but it requires a parameter. We are going to make use of our messaging class that we've constructed earlier on. Let's just get to that class itself. So messaging, it has an int pointer message sent method. So this method requires two parameters, the actual class receiving the message and the message itself. So to be able to access the message, we are going to need to create a selector. The key object that gives us access to the recipient will be this handle class, and then the selector we're going to need to create as well. The way we'll do this is to make use of the selector class, and we'll use the getHandle method on it. This getHandle will take a string as a parameter, so we'll pass in the initialize method's name, and then once we have that in place, all that's left to do is set the init method name again. So what will happen now is we'll initialize the underlying object, we'll receive a pointer back, and this is going to initialize our handle for this class. The question that remains now though is, will this constructor become available to the runtime? Would the runtime know that this will be the initialization for the class itself? And the answer is no, unless we export the initializer. So we're going to make use of the export attribute, and we're going to specify the actual underlying selector name. Notice that we use a string, so this means that we are going to point to init, and this is going to allow us to make sure that this constructor now become known as the init selector for this class to the underlying ObjectiveC runtime. Here is an example in which a CSharp method named setText is exposed to the ObjectiveC runtime. The string value of this attribute becomes the ObjectiveC compliant method name and will adhere to all the aspects of an ObjectiveC method which we've discussed so far. Notice how this includes the ObjectiveC method definition with parameters. The export attribute is also used to expose properties of an NS object derived class to the ObjectiveC runtime. In this example, the ObjectiveC property is named active. This export will typically create inferred methods from the property name, leaving us with a familiar property getter and setter implementation for C#. Let us explore setting properties in our class. Now, if you guys remember, we set 3 properties on our view controller. We set minimum value, maximum value, and limit value. Now I want us to implement min value and max value. Let's see how we're going to go about that. The first option that we have is to specify the property. So let's do that. We're going to set a public virtual property. Remember, these properties can be overridden. So we'll start off with a float. So in float, and we'll call this, let's call this max value. So once we have the max value in place, we're going to set a getter and we'll set a setter. Now, we want this implementation to auto-infer the methods or the messages that's going to be executed. So we'll use export and we're going to set the actual selector's name. And again, it's going to be a string that gets set. So this is going to be max value. Now, if you're worried that this is not going to give you the correct implementation, or if you find out that the inferred methods or selectors that's going to be used does not work for you, then we have the more verbose setting of a property. The more verbose setup looks like this. We again are going to set our property, standard C# property, and again it's virtual because we are going to overload this or override this. We're going to give the user the option to do so. It's going to be an n float, right, so that's our type. Then we're going to set this as our minimum value, and then we're going to implement the getter and setter. So this is going to be proper implementations. That looks like this. Now the question is, how do I complete this? What will be the messages that I'm going to call? Well, from the getter's point of view, we're going to return a value, and we'll do this by using our messaging class. So we are going to make use of a message, but this time around, this message needs to return a float. So you'll see the override that's going to closely match our options will be in float ObjectC message sent. Now, as before, we need to pass in a handle. Then we're going to need to pass in the selector that we want to use. So we'll use the selector class and the getHandle method. In terms of specifying the actual method call, we're going to use value, min value. So that's what the property looks like. But since our properties get synthesized, right, so they basically get set up, the setter is going to look a little bit different. The setter, since we are going to execute a method, will take a parameter. This means that my set implementation is going to look like this. API definition, messaging class, then we are going to execute a method that returns void. So we can't use a pointer, bool, or float. We're going to have to look for something that is a void implementation. So void ObjectC message sent would work. We are going to also pass a parameter. So this method won't cut it. We are going to need to pass a parameter, and then we have message sent in float. That's going to be the one to use. Like before, we're going to make use of this handle. We're going to get the selector, in this case getHandle, and here we have to specify the method. Now the method that we're going to call here is set min value. So you can see how the actual selectors differ. One is just going to return, this one's going to allow us to set a value, but since I have to pass a parameter, we're going to make use of the colon notation. So this means that this message or the selector set min value will receive an object. Now, this is in line with what we have, so we're going to have to pass the argument, which will be the value to the setter. At this point, this code will execute as expected. The only problem that we have is that we still need to export both of these getters and setters. So how do we do this? If we have a registration like this, we probably will have to do the same kind of thing down here. So the approach is the following. You are going to export the getter in the same way you've done up here. So we're going to specify that whatever needs to be executed here is going to be not the max value though, but the min value that we have. And then we're going to have to export the setter as well. So the setter will export this selector, the one with the parameter specified. At this point, the runtime will now recognize the selector min value as well as the selector set min value with a parameter. At this point, we have enough information to try this ourselves. Let's jump into an exercise and see if we can bind an ObjectiveC class library. In this exercise, we would like to bind this weather gadget library. What you'll notice here is that we have a dummy implementation here of a service, which allows us to get weather information. We're also able to light up a buzzer as well as an LED on this demo device. Now, the object that we want to bind by hand is actually going to be this weather file. So the actual weather class itself. It's not a complex class. It's going to allow us to set up a default constructor. So we would be able to implement that in it. And then we have this current weather property that we will be able to send. Now, if we look at the header file for this, you'll notice there's the property as exposed, and then there's our weather interface, the actual class itself. So this is what we would like to bind. Now we're going to switch gears. We are going to move into our IDE, CSharp IDE, Visual Studio for Mac, and then we'll complete the binding in there. Inside Visual Studio, we're going to create a new project. This will be an iOS application single view app. Remember, we're going to do a binding by hand, so we're not going to choose a binding library project type just yet. We are going to do that in IOS450. For now, we are going to do everything by hand. So please make sure that you choose a single view application, tap on next, and then call this project binding by hand. We are going to drop this project, or at least I'm going to drop this onto my desktop. And once I have it there, and I've created the solution, I'm going to add in two assets. So we need to set up some boilerplate functions in this project. So the first step is to add in, from your assets folder, the libweathergadget.a file. So this is our static library that's going to be used inside the project. Let's do that first. Once you've copied the file to your solution, make sure that the build properties for this file itself is set to none, or the build action. We're not going to build this file or apply any action to it. Once that is done, I want you to add from the assets the messaging.cs class. So this is our Invoke file. Well, you notice that we've had a look at this file earlier on today. In here are all our ObjectiveC message sent invocations, and these are the common ones that we'll use inside this project. There's actually a couple extra items in here. So basically, again, just boilerplate code that we'd like to use. All right, with that out of the way, the next step is to decide on the object we want to bind. Now, if you remember correctly, we've decided that we'll only bind the weather class itself. So what I'm going to do is add a new file to this project. It's going to be a simple, straightforward, plain old C# class file. I'm going to call this guy weather. So this is going to give me a weather class like this. Now the thing that we need to keep in mind at this point is that this is just a C# system object. We have to implement NSObject as the base class. So once you've added NSObject, we are going to make sure that we include the using foundation statement. Right, so the NSObject is defined in foundation. And with that in place, we will have this object exposed. The problem though is that there are two things that needs to happen. By default, what will happen is this class itself will only be exposed by name binding by hand __ weather, which isn't ideal. That's not what we're aiming for. Also, we are binding an existing ObjectiveC class, so we are going to need to specify with the runtime that this is actually a registered class that is a wrapper for an existing object. To make sure that we have a proper registration, we're going to make use of the register attribute. Now the register attribute has two specific functions here. First, we're going to make sure that we specify the name to our class. So this is how we want this exposed to the ObjectiveC runtime. Next, we're going to specify that this, as part of this registration, this class actually wraps an existing class. Right, so we set the second property there is wrapper to true. With that set, we're now able to instantiate our object. Now, what we need to keep in mind is that we are going to make use of NSObject as our base. So we need to instantiate NSObject in one of four ways. Either an empty constructor with a pointer, an NSObject flag, or a handle with allocation. Now we're going to choose NSObject. So NSObject, let's just get that flag there, set this to empty, and then once that's in place, we need to now make sure that we initialize the underlying ObjectiveC class. Now to do this, we're going to make use of the init or initialize handle method that's available on the ObjectiveC NSObject that we have. So initialize handle, let me just spell this properly. Initialize handle requires me to set two parameters. The first parameter is a pointer. So I need to somehow return a pointer to this class after I've initialized it. Then I need to specify the actual method that's called. In this case, it'll be init. So let's see how we'll implement and return a pointer. The way we're going to do this is now to make use of our messaging class, the one that we've introduced from our assets. Now this messaging class has preset p-invokes, and what we're looking for is to return an int pointer from ObjectiveC message without any parameter set. So we'll use that implementation. Now we need to specify the receiver and we need to specify the selector. The receiver is this class. Right, so it's the one that I'm wrapping. Then I need to specify the actual selector. Now to get an instance of the selector, we're going to need to make use of a class called selector, and we've seen this in our slide deck. But I need to show you where this actually resolves from, because at this point, let me just quickly complete the actual method we want to call getHandle. If I do this, we specify init here, so that's my selector's name. You'll notice here that this doesn't resolve even if I do a quick fix. It's going to give me some options, but these aren't the ones I'm looking for. So what we'll do is make sure that we'll use ObjectiveC runtime as our including statement. So we're going to using ObjectiveC runtime, use that, and that's going to make sure that we resolve the selector. Now at this point, after I add a semicolon, we should be able to compile the code that we have. So I'll quickly do a build here. And then with that in place, we should be able to drop into the view controller and instantiate this object. So if I create a weather class, let's call it my weather equals new weather, I should be able to get an instance of the object. So let's see what happens here. And I want you to take careful note of what the actual result is. I'll build the project, everything turns out to be okay. Next, we'll be able to run the project into the simulator. So let's do that and see what happens now. We should see the object being instantiated, and we should see that the application does not crash. Now, at this point, we need to start searching for a solution, because there's one or two things that might be problematic here. First, I want you to notice that we don't have an export on this constructor. So we're going to need to fix that first. So we'll use export. Then we need to specify the actual selector. In this case, it's going to be init. Right, so that's the first step. The second step, though, is to say, well, okay, let's see if this now works and try and run the application again. So deployment. Application starts, but it crashes. Now at this point, things become a little bit obscure. We need to figure out what is missing. So this message tells me that the native type NSObject could not be found, so we could not initialize it. There's a failure there. Now, it is not intuitive in terms of what we're doing, where this problem resides. But the ultimate problem, the underlying issue that we have, is that we're not loading this library into the application, we're not linking it. Now this is something that ObjectiveC and the binding library implementation actually fixes for us on our behalf. And we'll see how the tooling is going to automate this process for us. However, what we will need to do is modify the project build properties. So you'll notice here when we go to the options for this iOS project, the iOS build option underneath build is going to allow me to specify things like the SDK version, the linker behavior, supported architectures, etc. What we need to do is we need to tell this tool called mtouch how to deal with the libraries we have. So we're going to pass it additional instructions. And what we're going to tell it is to say that we need to pass in GCC flags, so the GCC compiler, that we have a library that has to be loaded. And we specify the library name, libweathergadget.a. The instructions for this is included in our instructions for this exercise. So you're welcome to copy and paste that line of code. Right, with that in place, I click on OK. We'll see that this application now will execute into the simulator and it won't any longer crash. Right, so now we have a constructor, we're loading the library, and it seems as if the application is stable. Okay, this means that we now need to look at the implementation of the actual property that we would like to expose. So remember, this property was a current temperature property. So what I would like to do is grab my weather, access the property, set it a value, and then use a debug statement to find the actual result of that. And we have two options to go about this. The first option that we have is the shorthand export. So what we can do is create a public property. This property is going to be a virtual because we are allowing people to override members from our classes. We'll specify the type as double, and then the actual property name is current temperature. Right, something like that. Okay, with this in place, we can now use a get set, and we can use the inferred member implementation or message implementation by setting the export attribute. So our export attribute allows us to specify the selector's name as a string, and we're going to specify here current temperature. Right, so with that in place, let's make sure we have the proper spelling. With that in place, we should be able to, let's fix that up as well, we should be able to set this value and get a value back. Let's try that and see if this works out for us. So going back to my view.load, we'll grab the myweather property. We should now have access to current temperature, and we're going to set this to 99. Then I want to include a debug statement, so debug write line. If debug does not resolve for you, add a system diagnostics using. With that in place, we should be able to grab the myweather project and get the current temperature value. Okay, so let's see if we can get a result piped out in the output for us. Alright, so you can see there's the value set to 99. So that seems to work. But it could be that you say, well, you know what, Chris, you're just setting a get and set. There's some field that this gets set to. So let's be a little bit more explicit. Let's go and implement the getter and setters here. So let's do it this way. Alright, so this is the long method. Now, the way we're going to do this is we are going to return a value from a message implementation. So we're going to grab our messaging class. We are going to return a double. So we're going to send a message that returns a double. That's our implementation. Again, we need to specify a receiver. Now the receiver is going to be this class. And then we need to specify selector. And the selector we'll get via the handle. And it is going to be this current temperature. All right, so let's specify that. So now, without a doubt, when we call get, we're going to return this value. But we need to export this. We need to change the actual way that we specify our export. The export now resides on the get itself. It's no longer on the property, but on the get. So we're registering the getter and setter selector methods or messages. Right, this means my setter is going to look like this. I'm going to grab from the messaging class the specific Invoke statement that will allow me to implement a void ObjectC message send, but still send a double parameter or double as a parameter. Right, so this means I'm going to make use of void ObjectC message send double. We're going to specify this class, right? So that's my receiver. And then we'll use the selector getHandle method, and we're going to specify the selector here. Now, in terms of these methods, what's kind of interesting is that when you use properties in ObjectiveC, the property gets synthesized into a basic getter and setter, and the setter normally gets called a set whatever the previous property was, right? So we have current temperature and then set current temperature. Now, to specify that this ObjectiveC selector will accept a parameter, we need to use a colon. That means there is something following. And then we'll specify as part of the argument set or the parameter set for this ObjectC message, we'll specify the value that gets sent here. The last thing we need to do is we need to export the setter. So we've exported the getter, but we need to export the setter as well. And notice that this is an explicit export. So export will use this selector that we set up. So we're going to specify it. And remember, we need to pass a parameter. And that's basically all that's needed at this point. So this means from this point forward, we should get the same behavior as the shorthand property setup. So let's try it out. I'm going to run the application. And we should still see the 99 Fahrenheit being set, or 99 value being set, that float. Right, so you can see there is our value. So underneath, with the shorthand, you're going to see that your messaging will implement the synthesized inferred members that's on your ObjectiveC class. If you need to change it, this is the way you're going to go doing the longhand explicit declaration and export. In our first objective, we've decided to manually bind a CSharp ObjectiveC class. In this objective, we're going to look in more detail at what is a framework specifically and what kind of libraries are available to us when we start looking at binding libraries in CSharp. We'll look at the definition for a bindings library. We'll define frameworks, and then we'll investigate dynamic versus static libraries, both concepts that we've talked about earlier. And once we're done with that, we'll look at universal libraries and then how to inspect our libraries using LiPo, as well as NM, a tool to display symbol tables. Up to now, we have mentioned two terms to describe items you will be able to use in a binding library. That is, frameworks and libraries. Generally speaking, people will use both of these two terms fairly loose in a conversation, potentially exchanging one for the other. There is, however, a couple of differences between the two. A framework lets you combine a collection of resources into a single package. And these resources may consist of binary code libraries, header files, designer files, localized strings, and supporting documentation. The term library, however, refers to the combination of the binary code libraries and the header files. As a developer, you have the option to create two types of libraries. You can either create a static library or a dynamic library. A statically linked library is a library of object code which is linked with and becomes part of the application. Dynamically linked libraries are a bit different compared to static libraries. These libraries are loaded by the application as needed. A static library is linked into the target binary, which requires a new compilation of the target binary when changes are made. Let's look at this graphically. A static library acts as a container for a set of object files and uses the A file extension. At compile time, a static linker collects compiled source code, known as object code, as well as library code, and then creates a single executable file. This means the static library is distributed as part of the application. Once the application runs, the library code is loaded into memory in its entirety. Let's compare this to the dynamic library implementation. A dynamic library is a container for a set of object files and uses the dylib file extension. At compile time, a static linker collects compiled source code, known as object code, as well as library code, just as we saw with the static library. However, the difference comes in at what the static library does next. Instead of creating a single executable file including the library, now a dynamic library reference is added to the executable. At runtime, the application will rely on the OS kernel to use the dynamic loader to load the dependent library. In this case, the dynamic library the app was linked with. As you all know, code libraries are convenient ways to package and reuse components. They provide a portable way to encapsulate code in a single file, allow for inheritance and modification of these files, and permit distribution of discrete units of functionality. You can combine components from many different projects into a single code library. For example, you might choose a custom control from one project, a component from another project, and then put them all together in one single code library. There is, however, one big drawback. All files in a single code library must be written in the same language. If you were to stop me on the previous slide and say, hang on, we have C#, F#, and VB.NET, and we are able to share the libraries created in those languages across the languages, I would probably have to agree with you. So we need to dig deeper into this concept of libraries and what is meant by choosing the technology stack and the libraries that are created. Because what you'll hear is that people will talk about managed code, and this is typically going to be C# in our case, or unmanaged code, which will typically be ObjectiveC, C++, C, or even Swift. And then we have another term, native code, code that runs directly on the operating system. And the problem here is that these three terms are used very loosely, and we need to understand the scenarios in terms of how they get used. Machine code is what Visual Basic.NET, C# and F# compilers create. It compiles to intermediate language, not to machine code that could run directly on your computer. The intermediate language is kept in a file called an assembly, along with metadata that describes the classes, methods, and attributes of the code you've created. This assembly is what is deployed in the .NET world. You package or copy the assembly to other devices to deploy the assembly there. Managed code runs in the common language runtime. The runtime offers a wide variety of services to your running code. When an assembly is executed, the runtime first loads and verifies the assembly to make sure that the IL is valid. Then, just in time, as methods are called, the runtime arranges for them to be compiled to machine code suitable for the machine the assembly is running on. Normally, this machine code is cached to be used the next time the method is called. This is where the term just-in-time or JIT compilation originates from. In the meantime, the runtime continues to provide services such as security, memory management, and threading as the application runs. The application is therefore managed by the runtime. Unmanaged code is what you used to create before Visual Studio 2002 was released. Visual Basic 6, Visual C++ 6, C++, or even ObjectiveC all produce unmanaged code. Code written in these languages compile directly to machine code to run on the machine where they are compiled, or on other machines as long as they have the same architecture. Unmanaged code do not get services such as security or memory management from an invisible runtime. These services come from the operating system, explicitly asked for by usually calling an API provided by the OS. Luckily, concepts such as Platform Invoke exists, which will help you consume these unmanaged libraries. And then we have native code. The phrase native code is used in two contexts. Many people use it as a synonym for unmanaged code. This is code built with an older tool or deliberately chosen in Visual C++, for example. Code that does not run in the runtime, but instead runs natively on the machine. This might be a complete application or DLL that's being called from managed code using Invoke. The second context is used to describe the output of the JIT compiler, the machine code that actually runs in the runtime. It is managed, but it's not IL. It is machine code. Good examples of this is Xamarin iOS, Xamarin tvOS, and Xamarin Mac. Each of these instances uses Mono and is compiled into a native binary. Another good example is UWP using .NET Native. As a result, don't just assume that native equals unmanaged. Due to the fact that different CPUs have different instruction sets, binaries must be recompiled for the target architecture the library will be used with. A processor or CPU is tasked at performing several tasks at any time, which may include communication with peripherals and devices, providing timing signals for code execution, the direction of data flow, as well as performing computer tasks as specified by the instructions in memory. On the previous slide, I've mentioned an important aspect in terms of code targeting a specific architecture, especially if you look at the way you develop iOS applications. When looking at the supported architecture options available for iOS applications, up to recently, we had the following CPU architectures to choose from. These options allows us to build for simulators and devices. When creating libraries or executables, we normally target either a simulator or a device. This process makes management of the development process a little bit cumbersome. If you are including external libraries into your project, you need to constantly reference the corresponding architecture version of your library depending on the deployment target. And the question that comes up quite often is, what if I could somehow combine these two binaries into a single file? And the answer is yes, you can. Combining different architecture binaries or multiple instruction sets is possible by creating a fat binary, also known as a universal file. And there's specific tooling that will help us with the process. To manage our build process, there are a couple of OS X and Linux command line applications available to use. The first application we're going to look at is called LiPo. LiPo is capable of listing the architecture types in a universal file, creating a single universal file from one or more input files, and then LiPo allows us to thin out a single universal file to one specified architecture type by extracting, replacing, and or removing architecture types from this file to create a single new universal output file. In our project, we've used libweatherGadget.a, and we just assumed that this gadget, or at least that static library, has all the architectures available for us to use. Let's go and inspect that library file. Now, if you want more information about LiPo, you're welcome to go and type in man LiPo, which will give you information about the project itself. Man is the manual pages command, and LiPo is obviously the command we would like to run. You'll see here this is going to give you a bit of information about what can be done with LiPo. Now, for our purposes, all we're going to do right now is to type in LiPo-info and then the library name itself. And as you can see, this architecture, or the architectures rather included in the file, is x86-64 and ARM64, which means we have a fat file. So this means that at this point, we would be able to use this library on a device as well as on the simulator, as we've done so far. When working with already compiled binaries, LiPo is key in the initial discovery phase. Since you will not be able to use a simulator targeted binary in a device targeting application, you will use LiPo to confirm the binary target. In this first example, you'll notice that we use LiPo with the info parameter plus the file name that you would like to inspect. And the output result here shows us that this file is not a fat file. It does include x86-64, but that's the only listed architecture type. In our second example, you will see that this file is a fat file. In here we have three architectures listed: ARMv7, x86-64, as well as ARM64. Definitely a fat file to use for both simulator and device targeting applications. Using multiple binaries when developing your application is cumbersome. For example, targeting a simulator build requires all resources to be the same architecture type. As luck may have it though, it is possible to combine multiple architectures into a single file. Here's an example. We're going to use LiPo to create a single binary as we've seen in our example so far. And the result of this would be a binary including 3 architectures: ARM version 7, ARM64, and x86-64. The parameters for the LiPo command in this scenario is create, which is going to specify that we'll use a set of input files to generate another file. We specify this file with the output parameter. Something to keep in mind is that you are able to create fat binaries using Xcode by adding additional build phase steps to your Xcode project. LiPo also allows you to strip binaries from the combined file. When submitting applications to the App Store, you do not want to include unnecessary library architecture types. This example shows you how you would be able to strip i386 and x86-64 simulator binaries from your overall library. One thing to keep in mind is that this process is purely for management of the unmanaged code libraries. This step does not replace the monolinker functionality. You will still need to run that on your overall application to reduce the overall application size before submitting it to the App Store. As the next step, I would like us to inspect the removal of an architecture from a file. So the first thing we're going to do is we'll rename this gadget file. We want to recreate this by replacing or removing one of the architectures. So to do this, I'm going to call it lib_whethergadget2.a, and that's going to give us a version which we now can pass into LiPo. So the LiPo command to use will be LiPo, specify the gadget file that you want to use, or at least your static library. Then we're going to specify the remove keyword, the architecture we want to remove. So in this case, it's x86-64. And then we specify the output file that needs to be generated from this command. In our case, it's going to be lib_whethergadget_a. Once you've run the command, we can now inspect that newly created static file just to make sure the architectures that are included excludes x86. Right, let me just make sure that I get the proper gadget file referenced here. There you go. So you can see at this moment, it's the architectures that's in this file is ARM64. Right, so there's no simulator build, which is going to be interesting if you think about it, because what we can do now is remove this whethergadget. Remember, we copied it into our project. Let's delete this and let's re-add this guy. So add files. We'll grab from our assets lib_whethergadget_a, open this up, copy it into this project, then we can build. All right, so I'm going to rebuild by my binding by hand project. And at this point, it's going to build proper. There won't be any issues. However, look at what happens when I try to run the application. The application crashes, and you'll see we are back to the point where we see that we can't load this file. So we can't recreate an NS object. Now, this is kind of interesting because when we saw this last, the process to fix it was to add mtouch arguments. But what's going on now? We have a real problem. How do we resolve this issue? Now, this is sometimes a little bit hard to figure out, but there's another tool that is going to come to our rescue, and we'll talk about that next. You've now seen how to use LiPo. At this point, let's jump into an exercise, and we'll compile an Xcode library. We'll create a simulator build, we'll create a device build, and then we'll use LiPo to create a fat file from both of those two architecture versions. When you open up the assets for this exercise, you'll notice that we have an Xcode project which we are going to compile. But before we do this, I want to show you the completed code, or the completed version of this exercise. You'll notice that we have an iOS phone build and we have an iOS simulator build. Each of these two builds will result in a library. I want you to look at the size of each of these libraries. The phone build is about 32 kilobytes, whereas the simulator build is about 28 kilobytes. Combined, these two end up being a 60 kilobyte file. If we include this into our binary, there's going to be a potential of 30 kilobytes of unnecessary code that won't be used when we publish this application. And that's the primary reason why we're going to use LiPo to strip out unneeded libraries. But for the development process, having a combination file is actually quite beneficial to us. Let's jump to Xcode. In Xcode, you'll see that once you open up the project, you might see something similar to what I have on my screen. There are two things here that's kind of interesting. First off, if you haven't built the library yet, you'll see that the products section will have the library name in red, which means it's not available, or there was an error in terms of compilation. The next item that you want to look at is the configuration choice. You'll see that from here, we'll choose the gadget itself, and we'll then be able to choose a simulator or a device. I want to start with a simulator. I've chosen iPhone X, and when I bold this, you will notice that we are going to get this item turned to black. So I'm going to select Product and Build. Once the build succeeds, that turns to black, and we'll be able to find this file in our Finder. Now I'm going to choose to copy the debug iPhone simulator folder that we see here. That's the product result that we have. So I'm going to copy this. Let's just get copy, and I'm going to drop it in my project folder here. Right, so let's paste the item right there. Now with this in place, we can switch gears and build for the device. To build for a device, you're going to plug in a device and choose the device as a configuration setting. You may at this point need to set up a provisioning profile. There is, however, a couple of instructions in the exercise itself should you want to fix this up yourself. Now, what we need to do here is, again, like before, pick the product option and build the solution. Once the build succeeds, you'll be able to resolve this in your Finder, so show in Finder, and you'll find that there's now a debug iPhone OS folder, and inside it is the library that we're looking for. I'm going to copy this and drop it into our folders here. So now we have the two binaries available, and we're ready to jump into our console to set this up. Once you have your console and you've changed to the directory that you want to use, quickly do a double check, and let's do an LSLA just to make sure that we have the actual folders in place. So you'll notice here, there's my assets folder, there's the completed folder, and there's my debug iPhone, iOS, and iPhone simulator. Now what we want to do at this point is to make use of LiPo and create a single binary. So I'm going to use the LiPo command, specify the create parameter, and then I'm going to include the files that I want to use. So the first file we want to use here is from the iPhone OS, and we're going to search for that library. So basically just starting the name and then typing tab is going to give you the actual input. Next, we want to include the debug iPhone simulator build. So iPhone S simulator is going to give me that folder, and then again I'll just be able to use the library's name. Now I want to create this library, the FAT file, locally inside this directory right here. So to do this, I'm going to just grab the next parameter that's going to allow me to specify the actual output file, and that's the output parameter, and then I'll use the name of the library I want to create. In this case, I'm going to copy and paste library with a gadget.a. So executing this is going to give me a new library file, and with that in place, I'll now be able to choose or have a look at the actual file and the included architectures. So to do this, we'll use lipo-info, choose the library file itself, and you'll see here we've combined x86-64 and ARM64. So what are the architectures for each of those two folders? Let's have a quick look. I mean, nothing's going to prevent us to quickly check. If I look at the debug folder, and let's start with the iPhone OS, lib with a gadget, you'll see that's the ARM64 version. And if I change this to simulator, let's see, iPhone simulator, you'll see that's the x86 version. Now there are other tools available to us as well. For instance, you could use file. File is going to give you information about the file as well. And you can see it's going to show me that there's a architecture, x86, 64, and ARM64. So a lot of tools are available for us to inspect these objects, but LiPo is going to be the key go-to tool to create and remove architectures as needed. You would have noticed that we ran into compilation errors trying to compile for an architecture that is not included inside our library. Now, to understand what happens at that point and to be able to fix the problem, we need to understand what a symbol table is. A symbol table is a data structure that is used by the compiler to associate attributes with identifiers used inside an application. So for example, this table will show us constructors, it'll show properties, and it will also show members that are usable. And armed with this information, you will now have a good idea in terms of what is available and what would be potentially missing inside your application's library. At the time of linking, the compiler matched the symbol table to the library members used in your application. If any member is missing, you will either run into runtime exceptions, which means your application will be crashing, or a more descriptive error message in the IDE if you are using a binding library project template. You would agree with me that having a message in the IDE is much more worthwhile than just seeing your application crash. However, you will only see the message that I display here on screen when you have a binding library project template, which means in our scenario at this point, we need to have another way to look at what potentially is missing from our libraries. Luckily for us, we have a tool available to allow us to inspect our binaries. The application you would like to use is called NM. NM allows you to inspect and display a name list or a symbol table for the specified binary file. Our command line allows us to specify things such as a search results order. Here we specify that our search results should return numerically. We are also able to include options like displaying all symbols for a specific target type architecture only. This will reduce the amount of output that NM produces. Here's an example of such a symbol table search result. As you can see, this will give you an indication of which types and members are available or alternatively, if not listed, missing from your library. Now, NM is going to return quite a big result set. If you want to filter the output, you can simplify your search using grep. Let's investigate this scenario a little bit further that we have. Currently, we have an application that has a library set for simulator build that is crashing. So what we can do is use NM to inspect our library file. Now, if we do the following, if we go and specify that we would like to search for a sorted list of an architecture type, we specify x86, 64, and our library name, you'll notice that NM is going to return that there's no architecture x86 inside that file. So that's the problem that we face here. We've stripped out all the symbols, which means if we to do something like this, change the build type here to a debug iPhone, and then select my device, we'll be able to run and deploy the application. So let's double check this. I'll build the application, deploy to my device. Now I'm not going to cast my device on screen, but you'll notice here that the bundle installed, and then we should get an output result. So having a FAT file is really beneficial for us because we don't need to switch between library copies. We use a single library to interact in a simulator as well as a device build. Now, one thing you need to keep in mind, remember that your configuration needs updating after each change. So for instance, you'll need to make sure that you do add the mtouch arguments. Let me show you. If I were to switch here to a release build for phone, and we have a look at our mtouch arguments, that setting is gone. So make sure that you update all your configurations so they are consistent across your configuration selection. Otherwise, you are going to, again, sit with a scenario where the file can't be loaded. But this time, it's not because there is no architecture, it's just because you haven't specified the mtouch arguments to link the specific file. Right, so be aware of those niggly issues that might pop up. In terms of rectifying the missing symbol scenario, there are a few potential steps you can take. First, you'll be able to check your binary architectures included. It might be you are compiling for device, but using the simulator binary. Alternatively, you'll be able to edit the source code and recompile the code. Most of the time though, you're going to have to go back to the provider of your library and make sure that you have either a FAT file or the specific library architectures to target a specific build type. In this exercise, we are going to look at the previously created FAT binary, and we'll use nm to inspect the classes and members that this library should expose. Back in our console, let's make sure that we have all the files we want to use. I'll type in ls-la. You'll see that there's the folder containing the iPhone build, and there's the phone containing the simulator build. And we've used lipo to create this file. Let's just double check and make sure that this is the file that we're thinking of. So running lipo info lib with a gadget, you'll see that it includes two architectures. All right, the next step is to run nm. Now nm, if you need more information about nm, you can go and have a look at the man pages. So man nm is going to show you a couple of options available to you. Okay, so with this out of the way, we can now go and search for our symbols. I'll use the sort numeric option from the command line parameters, and I'm just going to type in the lib with the gadget, the file's name. Right, so executing this, you'll see if I scroll back to the top that we have two classes exposed here. There's my weather class, and here is my weather gadget class. The weather class, if we look at the selectors here, you'll see there's an init, there's a current temperature, and there's a set current temperature. So this is interesting. The reason why I say this is interesting is you would have remembered there that we add only a current temperature property, but when this gets compiled, that actually gets synthesized, as I've mentioned, into these two selectors. And if ever in doubt, have a look at nm, because it's going to give you these results. You'll be able to figure out what's cooking in terms of the API and how to use it. That's now to say if there is no documentation available. Generally speaking though, this is standard inferred members, and that's why the shorthand export on properties worked for us earlier on in this course. Scrolling down, we have the weather gadget. Now we're not binding to it, but if we were ever to do so, you can see all the APIs exposed. There's my messages, and there's a block, and we'll be able to dig into those. There's also the delegate that we are able to use. Right, so that's nm and the results that we were looking for. In this course, I described what is involved in manually binding an iOS library, and you were able to create a simple class binding yourself. I looked at the NSObject class as well as the Xamarin iOS type registration system. You saw how the type registration system attributes are used to achieve class and member registration for CSharp classes within the iOS runtime. I also described the main differences between the library types you use in Xamarin binding libraries, comparing frameworks and libraries, and discussing static versus dynamic library usage. You also saw the use of applications, which allows you to inspect the binary libraries you use in your binding projects. Thank you for joining me in IOS450, building an ObjectiveC bindings library manually.